Hi, so this is a very short lecture covering the last portion of chapter 3 of our textbook. So this will be a pretty brief lecture compared to the previous couple of lectures. So here I want to cover the various issues pertaining to electrostatic potential and the electrostatic energy. So let me begin with the definition of the electric potential that I have visited several times already in this lecture, and that's the potential given as the integral over some charge distribution divided by the distance factor and integrated over all space where these first charge distribution resides. And so I have explicitly indicated this charge density with a index 1. And the potential due to the first set of charge distribution is labeled also by the same index 1 right here. So now I'm going to assume the existence of another set of charge distribution now given by a different function, which I label as a rho 2. So pictorially, the situation I have in mind is you have a cluster of charges over here that's described by one kind of potential, one kind of charge density function, rho 1, and you have another cluster of charge described by a second charge density function, rho 2. Okay, so this rho 1 distribution creates some sort of electrostatic potential around it, and that affects the charges residing over on this side and give rise to some energy felt by the charges over here. So the potential energy, according to the standard definition, is just the potential, electrostatic potential multiplied by the charge. Or in the case of a continuous distribution, it's the charge density multiplied by the local electrostatic potential integrated over all positions where such charges reside. So the potential energy will be given by this integral of the second charge distribution function multiplied by the electrostatic potential generated by the first set of charge distributions over here. And when you combine these two expressions together, the overall result will be this highly symmetric form where you have a product of charge densities from different objects, and they are weighted by this inverse of the separation. And then you just have to integrate over both the locations of the first charge density and as well as the second charge density. And the successful evaluation of this double integral will be able to tell us exactly what is the potential energy of this particular charge distribution over two different objects. Here you come up with a seemingly trivial observation, which is that you can interpret this double integral either as the electrostatic energy due to the first charge distribution felt by the second charge distribution, or vice versa. Namely, it can be interpreted as the potential energy felt by the first charge distribution due to the potential generated by the second charge distribution. Okay, so what I mean is that this formula, being due to its symmetric nature, can be interpreted either with the labels 2 and 1 or with labels 1 and 2. And this seemingly trivial observation apparently was due to Green, who was sort of mathematician slash physicist. I believe in mid or late 19th century, and this is called the Green's reciprocity theorem. Okay, so sometimes this reciprocity theorem finds useful applications in the evaluation of the potential energy, and there are some examples of application of this theorem in our textbook, which I won't go into, but you're welcome to look through those examples in your on your own initiative. Now, there's also a self-energy version of the electrostatic energy, which is coming from having the same charge distribution function for both rho 1 and rho 2. So here the assumption was that rho 1 was for one kind of object and rho 2 was for a different object which is separate from the first one, like this. But if you have only one object which is charged, and that object is described by the charge density function rho, then you can write down this sort of energy function where both rows pertain to the same object. And just to make sure that we're not double counting the energy, there has to be this factor of 1/2, because as you integrate both over r and r prime, apparently you're counting the same pair of charges twice, and you don't want to do that when you evaluate the energy. So that's why you have to put in this 1/2 factor explicitly. And this energy has a nice interpretation as the energy required to assemble this particular charge distribution. A good example is if you have a spherical charge and in the form of a sphere having the radius r, and for the sake of simplicity, let's assume that the charge density is uniform all across the sphere. So then the charge density would be some constant, like the total charge divided by the volume of the sphere. Okay, so if we can manage to perform this double integral, that would mean that we know how much energy is required to assemble charges into the spherical shape having the radius r. And that means that boils down to whether we can perform this sort of double integral. And apparently it looks pretty hard. So at first sight, it's not even clear that one can even perform this double integral easily. So the first try, which is the most naive approach to evaluating this energy, seems to fail. But there's a more clever way, and that is by following the interpretation of this self-energy as the potential phi multiplied by the charge density and integrated over all space. And of course, we should not forget this 1/2 factor just to avoid the double counting. But now this potential is quite easy to evaluate, because for spherically symmetric distribution of charge, we can invoke Gauss' theorem to evaluate the electric field as a function of the distance from the center of the sphere. And using that information, we can evaluate the potential quite easily. And once you go through that exercise, the result will be exactly this thing: the charge density multiplied by distance squared divided by 3 times the electric constant. Okay, good. So now that we have this information at hand, we can just insert this expression back into the formula for the potential energy, and just perform only one more integral, and that's quite easy. So if you do that, then the result is after a slight amount of algebra equal to something that actually looks pretty familiar. It's just the charge squared divided by 4 pi epsilon r. And the only real non-trivial aspect of this formula is this 3/5 numerical factor, which kind of reflects the geometrical shape of the sphere. Otherwise, everything else is sort of predictable from purely dimensional argument or dimensional grounds. So I think at the turn of the 20th century, as people began to realize there is this elementary particle called the electron, they wanted to think of an electron as a spherical ball of some tiny radius r, whose charge equals the electric charge that was being measured. So then they try to apply this formula to interpret this energy as the energy required to assemble a single electron out of nothing, and that interpretation basically did not really work out very well. But for historical trivia, it's perhaps useful to remember that people were seriously thinking about applying this sort of formula to associate some sort of electrostatic energy to the electron itself. And I think there were even attempts to equate this thing to m times c square, okay, where m is the mass of an electron and c is the speed of light. So by equating this electrostatic energy to the rest mass energy of an electron, people try to deduce kind of an estimate for the radius of an electron, which, as far as I know, never really worked out. Okay, but people are granted such freedom to play around with various ideas, and not all interesting ideas lead to fruitful results. And perhaps this was one of those instances where ideas seem kind of interesting, but in the end did not lead to any fruitful conclusions. Okay, so I thought I would just mention that. And the other interesting piece of theorem that you might associate with this self-energy form is that this self-energy has always to be positive. And so first let me present the proof, which comes from invoking the Gauss law. So according to Gauss law, the electrostatic potential phi, when you apply a Laplacian, becomes equal to local charge density divided by the dielectric constant. Applying that result the other way around, you can rewrite the charge density as some factor times the Laplacian of the electrostatic potential. So now this integral involves two terms which are both some functions of the electrostatic potential. But clearly you can integrate this integral by part, and one of the differential operators then will act on this second potential. So now you have a more sort of symmetric looking expression, which is a gradient of the potential squared. But gradient of the potential is nothing but the electric field. So the electrostatic self-energy turns out to be equal to some numerical factor times the electric field squared integrated over all space. And since you're integrating something which is definitely positive or at least non-negative, then the integral must also be positive. And which makes sense. For example, let's say if you want to assemble charges in the shape of a spherical ball, then since you're assembling charges of the same sign, then you have to overcome their repulsive force to force them literally to take on the shape of the sphere. So you must do work to assemble the charges into a certain shape, and that means creating such a charge distribution will cost you a finite amount of energy, which is positive, not negative. So this identity, this theorem that the potential energy of the self energy of a charged object has to be positive, does make a lot of physical sense. And the other important finding from this simple exercise is that you can really think of this thing inside the integral, which is 1/2 dielectric constant times electric field squared, as the energy density. So by integrating the energy density over all space, you're obtaining the total electrostatic energy. And this interpretation of this particular expression of electric field squared as the electrostatic energy density will play a pretty important role in many aspects of electrodynamic theory. And even into quantum theory, this expression basically survives and plays an important role in considering things like electromagnetic fluctuations using the quantum picture. Okay, so anyway, let's try to keep this expression in mind, and that should conclude pretty much everything I want to say about chapter 3. So hopefully in the next lecture I will begin to talk about stuff in chapter 4, which is a chapter on electric multipoles. Okay, so until next time.